Hello, we are Team 9 and welcome to our project demo for the identification and monitoring of operational modes in machinery. Our project aims to solve a problem present in monitoring the condition of machinery, that the sheer quantity of diagnostic data outputted by a machine is too high for any given person to be able to thoroughly analyse it. Additionally, because degradations in the machine's condition over time can be very subtle, the patterns they cause can be difficult for a human to recognise. Our solution to this problem is to use a machine learning model to monitor the diagnostic outputs of a machine and to alert the operator when anomalies are detected. This then allows preventative maintenance to be performed that can both improve the lifespan of a machine as well as potentially preventing catastrophic failure. The first screen the user sees when they enter the app is the login page. In the centre there is a button that redirects them to Intelligent Plant's login system. The user can then log in with their preferred provider. The machine screen displays the machines that the user has registered in the app. Each machine has its name, how many anomalies it contains, and the time of the most recent anomaly. The bell icon in the top right of each card allows the user to opt in to email alerts about detected anomalies on that machine. The toolbar at the top of the screen allows the user to search through the machines by name as well as by sorting the number of anomalies present on the machine, the time of the most recent anomaly, or the time of the oldest anomaly. The user can also select the machine by checkbox in the filter drop-down if they wanted to have more than one machine selected at once. After clicking on one of the machine cards, the user is directed to that machine's anomaly screen. This displays a breakdown of the anomaly groups present on the machine. An anomaly group is a set of anomalies clustered within a relatively short period of time. Each anomaly group contains a count of how many anomalies were detected within that time frame, as well as the time of the first and last detected anomaly. Like the machines, the anomalies can be sorted by count, most and least recent, and longest and shortest time taken. They can also be filtered by the type of anomaly: pump, system, or system and pump. When the user clicks on an anomaly, they are taken to the graph screen. This contains a list of parameters on the left that can be selected for display on the graph. The vertical yellow lines on the graph represent anomalies positioned at the time of occurrence. All data points are plotted as percentage change due to the difficulty of combining more than two different units on one plot. The specific percentage value of a data point can be seen by hovering over the line. Lines can also be highlighted by hovering the mouse over their parameter on the left. Jing will now demonstrate the anomaly detection in more detail.
Now I'm going to show the running demo of the Python backend. First, let's get the Flash service running. Then I'm going to use the Postman to demonstrate the working flow of the Python backend. As you can see here, the Python backend will receive data from the C# backend in the CSV format. Now the historical data has been sent to the Python backend. In the Python backend, the data will be pre-processed and will go through two different stages of the model prediction to predict the anomaly and its type. After finished prediction, the Python backend will send the response through the API. Here's the result. The output will be the timestamp and its anomaly detection result. The value will be none if there's no anomaly, and if there's an anomaly happen, the value will show the type of the anomaly, like the system. One special case is ambiguous. We suggest that the two stages of the model prediction have different results, and may need the user to check by themselves.
Thanks, Jing. Overall, we're really happy with how the project came together. A particular achievement was managing to coordinate a system written in 3 languages: Python, C# and TypeScript, which was necessary due to the languages that the components provided by Intelligent Plant were written in. Additionally, we're really proud at having managed to accurately complete a challenging brief encompassing skills from all areas of computer science. As a group, we see this product as a very strong first version of the application. However, with a further investment of time, we have ideas about where it could be built upon. Given more time, we would aim to allow the machine learning model to continually retrain itself. This would help counter the performance degradation of the algorithm that could occur over time due to natural changes in the diagnostic outputs produced over the machine's standard operation, and, given human input, would be able to improve the accuracy of the output by reducing the number of ambiguous outputs. It would also be interesting to expand the range of data visualizations available to the user to allow them to more accurately diagnose the source of anomalies. However, this would likely be outside the scope of the project and is already implemented by the application Gestalt Trend in the Intelligent Plant Industrial App Store. Thanks for your time watching our demo video.